Well, welcome everyone to this seminar lecture today. We are going to be discussing the origin of allometric scaling laws. We have seen this previously in our course, but today we're going to have a deeper look at this fascinating problem. In order to start this adventure, we need to go all the way back to 1932 with a professor called Max Kleber, who was a biologist, and he started studying metabolism. Metabolism understood as the amount of energy that an organism requires to intake constantly, daily, or whatever, so that it survives, right? And he did so for various different organisms, including metazoa and plants, and here is the kind of data that he obtained. So in this first graph, what we're plotting here in the y-axis is metabolic rate. So this could be understood like some energy per unit time, like watts, that an organism requires. And in the x-axis, he plotted this with the body mass of that organism in adulthood. Right? So for example, here we would have a small mouse, right? So that's low body mass, right? Then we have some metabolic rate. Here we have humans, and here we have an elephant, which is way bigger, right? And then he observed that there was this quite definite curve that trended upwards this way, a little bit curving that way, right, in this plot. And the genius of Max Kleber said, okay, let's do something here. Let's actually plot the same data, but now using logarithms. So basically, he took the logarithm of all the values on the vertical axis, the logarithm of all the values on the x-axis, and plotted it again, right? So this is exactly what he obtained. Now, here, all this data was sketched in a way that it perfectly defined a straight line. And this is a straight line that curves upwards with a slope that we are going to call it alpha. And what Kleber observed is that alpha was more or less equal to 0.75. Great, fascinating. This meant that we could actually define some sort of empirical law, right, that related the metabolism of any organism to its body mass. In other words, we could say that, okay, metabolism is somehow equal to some constant here times the body mass to the power of alpha. Why is that? Let us remind ourselves, we've done this several times, but let us remind ourselves that if we take the logarithm of this expression over here, what we see is that logarithm of b will be logarithm of b naught, this constant that I've just made up, right? Times logarithm of m to the power of alpha, but that's nothing but alpha logarithm of m. And this looks like a law that it's nothing but a straight line, right? So this is going to be a constant, right? Then here we have the slope. Let me call it b over here, just for similitude purposes. And this is exactly the equation of a straight line. And that's what he observed in his data. Okay, so from this argument, we go all the way to this law. That's great, that's fantastic. And this is how things kind of settled for a long time. We're talking about this was discovered in 1932, right? And all the way to 1997, this was just but an empirical law. But 0.75, it's kind of a funny number. As a matter of fact, 0.75 could be written like 3/4. And that made scientists go nuts about this. Why 3/4? Why not another funny number such as, I don't know, 0.82 or something like that? 3/4 looks like a bit of a round number, so maybe there's something lurking in here. And this was actually revealed in their seminal paper in 1997 by West, Brown, and Enquist, published in Science, where they found the reason why this 3/4 was always sitting there at Kleber's law, which was, until that moment, just an empirical fact. Today, we're going to discover how the scientists unveiled this mystery and how we came to understand way better what are the underlying laws of metabolism and other many implications that this kind of thinking has in modeling biology, right? Let's start with a question. Why 3/4? That's what the three main characters of this story started asking. Why 3/4? And they start thinking, okay, so metabolism. Metabolism is the energy input that you need to input into the system, into this organism in order for it to survive, right? But what is metabolism related to physiologically? Well, definitely metabolism must be related somehow to energy distribution, right? And distribution here being the key word. Okay, so any organism, in order to metabolize, it needs to distribute the energy around all of its cells. Great, but energy distribution is strictly related to vascular systems. So when they started thinking about vascular systems such as our blood distribution system, the circulatory system, right? They started looking at these funny structures that we now know very well that are permeating all of the organisms that we're talking about here. And they began thinking, okay, this is a very interesting structure, and actually it kind of looks like a fractal, right? So we're going to go back to this fractal idea later on, but this brought these three scientists to propose these two ansatz here that we're going to use at the end of this lecture in order to come up to an answer to this question, right? So the first ansatz here, the first hypothesis is, okay, so this irrigation system, these vascular systems are organized in a way that they optimize blood supply. So there's some optimization process here. Supply optimization, right? And this is achieved via space-filling fractals. Okay, so we shall need to use these ansatz at some point. And basically what's saying is that these systems are organized in a fractal way, in the manner of optimization, the supply of the blood flow. Great. There's another ansatz that they also came up with, and that's all the basically hypotheses that were required. The second ansatz here, the second hypothesis that they required was there will be some kind of an economy of tissue. In other words, I will try to economize all the tissue that I need to build up this system with, right? So there's an economy of pipe tissue, if you want. Let's quote unquote this. Such that the system becomes, again, sort of optimal, but in a different sense, optimizing here the materials that you need in order to build up the energy distribution system. Great, so with all of these ideas in mind, we are now going to explain why 3/4 is the factor that sits in this scaling law that Max Kleber first obtained in 1932. Great, so let's begin with how do we define this model. Remember, we want to somehow model all of this intricate system, which is a vascular system, right? But we need to do it in a way that we can dominate the problem. We can use mathematical tools in order to tackle it. So a good way of doing it is considering how all of these, if you want, branching out mechanism can be defined with sort of a recursive format, okay? In doing so, we start with the main artery here, which we could think of the aorta, right? And we say that this main artery will have some characteristical length, L0, okay, and some radius, R0, all right? In general, what we expect the system to do is to keep branching out in smaller and smaller pipes, right? So here, for example, we see how this first pipe, the bigger one, the aorta, kind of branches out in 3 different ones. Right? And then each of these 3 different pipes will branch out in 3 other ones, and so on and so forth. So overall, we'll have a certain number of iterations for this process. And we could enumerate these iterations with some index. We say K, right? That will go from 0, 0 being the main arteria here, the aorta. And then the first branching iteration, the second, the third, and so on, all the way to the last one, which we'll denote as N. N would be the last iteration process at which we should be reaching something like the capillary level, right? So each of the last tiny branching event will reach capillarity level, right? So remember that because we will be using this N accordingly with capillarity level. And that's great, right? So far we have introduced basically three things. First off, this index here that tells us at which branching state we are. Then we have introduced the length of each of the branches. Notice that I've used this index here in the subindex of L. So in other words, for example, if I take this branch and I zoom in, I see that these will have some length and some radius, right? And all of the different branches will have different radii and different lengths. Okay, so we shall talk about this a little bit later on, but now I want to focus on something very simple, and we've seen also this in other formats and in other problems during the course, but let's go again at some very basic tool here that we need to use, and that would be the branching number. So in order to model this system, we need to talk about a branching number. In this example here, I've used Q equals 3. This means that each of the pipes here will branch into 3 different pipes, right? And then again and again and again until the very end, until the capillary level. But I could have any branching number that I wish. For example, I could have Q equals 2, right? And I would have this dot here, which could be representing anything from, I don't know, disease spread, or again, some vascular system. Then it branches to 2 different ones, and then to 2 different ones, and then to 2 different ones, right? So Q will now be just a number. I'm not going to specify which number should be used for our vascular system, or general model vascular system here, but we need to bear in mind that we need to have this value Q in order to assess some of the features that come next, right? So we now understand what this Q is. It's just the branching number for this process, and we move on to start asking some interesting questions. The first question talks about fluxes, right? So there must be an initial flux here. There is some zeroth pump of energy that is being injected over here. And we use the letter Q for these fluxes, right? And I'm using the 0 in the subindex in indicating that this is the flux of blood, if you want, that it's entering the aorta, right? And this is all the flux that carries all the energy into the system that we have access to overall. And it needs to be distributed across all of these branching processes. Great, but that's interesting, right? Because our main problem here is to relate how this energy distribution is related to metabolism. Metabolism is, if you want, a global measure of how much energy is required by the organism. But clearly, this energy is related to the flux of blood that I can input into the system, right? So, in other words, we say that the flux is directly proportional to the metabolism. And we have established our first proportionality relation that we need to use all along this problem. So we need to bear this in mind, right? So the flux of blood that is entering the aorta is going to be directly proportional to the metabolism of the organism. Now, let us use the idea that this flux that is entering the aorta needs to be conserved, right? So there will be flux conservation. And it needs to be conserved across all of the different branches, right? So in other words, if I was studying the flux that it's going across a particular pipe, for example, this one over here, right? And now this flux is going to enter these 3 pipes, I know that all the flux that's entering over here needs to be the same flux as the sum of these 3 ones. In other words, what we can say is that this is going to be Q. Remember, Q is this branching number. In that example, it will just be 3 times Q BQ, which is the flux of the branches at level K plus 1th. All right? So if we understand this, and this needs to be preserved, we now can relate the flux in the aorta, for example, to the flux that we shall receive at the very tip, at the end of the capillaries, right? Let's move up here in order to see that. In other words, we know that this is conserved all the way down, so every time that I branch, I need to add a factor Q, right? And then I can keep on branching and branching until I reach the capillary level, which is the nth level in our index here. How do we do that? Well, we simply say, okay, so we will reach Q sub n if you want. That's the last flux that we have in this system. And I know that I need to add Q to the power of n here. That's this Q here iterated n times. Great. Actually, let me define the flux at the capillaries. let me define it as Qn. This is exactly the same thing. I just want to make a distinction here because we know that there will be limits stemming from the physics, the physics of fluid dynamics and tissue properties of the organism that will require this to have some particular value. And this cannot be just any value. If you want, you can think of this as some sort of a cutoff, and we will revisit this cutoff across the problem. But basically, in other words, what I can say is that now I have established that there is this relation over here, and this is just a constant, some constant that is given by the physiology of the problem. This is really interesting because now we have related, remember, the metabolism, which was directly proportional to the flux of the aorta, the main flux of the main artery that it's coming in, with the branching number to the power of n. In other words, I can say from this that the metabolism must be proportional to q to the power of n. Okay, that's fascinating. That's really, really interesting. Now let's do something else. Remember that our empirical law, our law that we need to establish here, said that basically B was proportional to m to the power alpha. And we want to know, we want to demonstrate that this alpha needs to be 3/4. That's the goal of this model, right? So we assume that this is true, and then we will show that alpha exactly needs to be 3/4. So if we assume that this is true, what we get is that we shall have this scaling relation between m to the power of alpha and q to the power of n, right? Because B is proportional to m to the power of alpha, B is proportional q to the power of n, just by this argument here of flux conservation. Therefore, we require this to be true. Now, this is something a bit tricky, but you need not to be carried away with this. But notice that this here is adimensional, meaning that it has no units. This is just the number. The branching number is a pure number, right? And n is the number of different branches that you stem from the very beginning to the capillary level, right? So this is just an adimensional number, but this is a mass. So this is kilograms, if you want, to the power of alpha. So this relation here actually is not entirely right. We need to include some dimensions, right? So in order to do that, you basically adimensionalize the left-hand side of the equation. And now this, we know that for some value m naught, it will be equal to q to the power of n. And it is required to be so in this precise way, right? Now, this is a dimensional, and from this equation, we can obtain an interesting relation that we will need to keep in mind and use later. So if we go up here, allow me to go up here, notice that if I take logarithms in both sides of this equation, I will get alpha logarithm of m over this adimensionalizing constant here that we just had to use, and that is equal to n logarithm of the branching number q. Great, we need to keep this equation in mind, and next we're going to study another property of this system which relates to fractality, right? And I will start sketching this over here. So we need now to think a little bit more about how our model is somehow established. And remember that these scientists were inspired by the idea of a fractal system stemming all the way through all the little places that the organism requires the blood supply to fill in, right? And as such, they said that this system, at least on average, represents a fractal, or if you want, a self-similar structure. Great. So how do we understand this from all the different variables that we have defined in our system? Well, we can begin by look maybe just at a particular branching point, right? So any branching point will suffice over here. Okay, there will be, if q were 3, we are not, remember, we are not saying that q needs to be 3, so this is just an example, right? We know that there's a pipe here that arrives here. This is maybe the kth iteration, right? And this then will be the k+1 iteration. Great. And we know that this has some radius, r sub k. And this one over here and all of the other partners, all the other sister pipes here, will have also r k+1, because precisely we are at the k+1 iteration. So we have this radius, but we are requiring this system to be self-similar. That makes a lot of sense also if you think about it from a biological standpoint. You need to utilize the same instructions over and over again, right? And so all of this kind of inspired the idea that I'm going to pose right now. So if you want this to be self-similar in terms of radius, what you need to say is that r of k plus 1 over r of k needs to be some constant that will necessarily be less than 1, so that this keeps getting smaller and smaller. If it was bigger, then the system would blow up, right? There would be no pressure in order to fill it. So obviously this needs to be smaller than 1. And we say that this is going to be constant across all scales. In other words, this is constant for all the different values of k. This simple expression here is telling us that this system is built up in a self-similar way. And we do the exact same with the longitude of each of these pipe elements, if you want. So if I say, okay, this is L sub k plus 1, this should be a bit longer, of course. So if this is L of k, I know that by this self-similar principle to structure, we know that Lk plus 1 over Lk also will be a constant value. We will call this gamma. And this will be the same for all the different branching processes that we have undergone. Great, so now with this in mind, we're going to turn to another scaling law. We are going to arrive at a different one over here, but instead of using just the simple flux conservation principle, we're going to use a different one, which is that the mass of the organism, the body mass, needs to be proportional to the blood of the organism, okay? And with that, we'll reach another equation, and we'll eventually figure out this problem. Great. So with all, now we are approaching ever so slightly to the end of this problem. Now we have already established this relation, right? And we have used, or we have introduced the idea of self-similarity in the construction of this system. Great. And now we're going to use the following idea. So the total volume, I'm going to use V sub T. This is going to be the total volume of blood, right? Blood or whichever fluid is circulating across this system. But let's say total volume or total blood volume, right? I'm going to air quote this just to say that this could also be established for plants, etc. But this is the fluid that you basically fills up all of this system. How do we find the relation for the total volume of this system, right? With all of what we have written so far. Well, the total volume of the system, I'm going to write it here, will be nothing but the sum across all the different branches. Remember, the branching index goes from 0 all the way up to n being the capillary index. So this is the very last branching that occurs, right? And here I'm going to write the number of elements, the number of branches that exist in the kth level, right? So for example, k equals 0, we know there's just one branch. So this, in this case, is the aorta, right? K equals 1 will be 3 if q was 3, just following this example over here. And then k equals 2 will be basically q squared. If we follow this example over here, it would be 9, right? So this would be 3, 3, and 3, 9, etc., etc. So this is this number here, n sub k. And the volume that is occupied for each of the elements of each branching level, right? Okay, so k equals 0 will be the volume of the aorta, k equals 1 will be the volume of the next step from the aorta, so this volume, and this volume, and so on. So we can rewrite these using some of the things that I've already said, right? So first off, this is going to be the sum from 0 all the way up to the capillary level, right? Of q to the power of k. Q to the power of k, why? Well, I said that this q, the branching number, is telling us how many branches we have at each stage. Again, 0 would be the order, so that this would be a 1. The next stage would be 3, the next would be 9, and so on and so forth. And then the volume k, we are going to be writing it just by looking at this picture over here. So we know this is a cylinder, and so therefore there's going to be a section here, and the section will have value pi rk squared, right? So this is the section, but we need to multiply this by the length of this cylinder here, and this is Lk. So this is exactly V sub k, right? And there will be q to the power of k as many elements at branch k of these ones. And we need to sum all across the different branches. Well, this is beginning to look a little bit difficult. However, we should remember that we have these self-similar expressions over here. So, in other words, for any rk, I know that this is going to be nothing but b rk minus 1, right? So this goes just straightforward from this relation over here, right? Exactly right, yes. But if I keep doing this, I'm going to end up with something like b to the power of k times r naught, where r naught, remember, is the radius of the aorta, the main initial artery. The same thing will happen for the lengths. Using the self-similar structure that we have established before, the same sort of thinking brings me to this relation. So in other words, the length at the kth level is going to be gamma to the power of k, the length of the aorta, and the radii at the kth level, it's going to be b to the power of k times the radius of the aorta for the kth level, right? So we can use this and plug it in here, right? So I'm going to be coming all the way up here, right? And I'm going to write this expression all over again with all of this knowledge. Okay? So we see, again, we need to sum this all the way up to n. And we have now, notice we have pi r naught to the squared, L naught. I'm going to bracket this out. This is going to just be a constant now. This is just the volume of the aorta. That's very interesting. We're going to call it V0, okay? To be consistent with all the notation. But we're left with all of these factors, b to the power of k, gamma to the power of k, and q to the power of k. Notice that b needs a square as well, because here we have rk squared. Therefore, to be truly exact, we need to include this square over here. That's all to the power of k. Well, this seems a bit cumbersome, but actually this is getting better and better, right? So now notice that this is a constant, so I can just put this constant outside, or in other words, yeah, sure, let's do it this way, and I'm left with this summation over here, which is a value to the power of k, and this is summed all the way up to n. This is a very common series that we have encountered in other subjects for sure. If you've never seen this before, there will be an appendix to this seminar that explains how to get to the next level, to the next step over here. But simply, this series can be summed. It's a finite series, so it definitely can't be summed, but it can be summed in some like elegant closed form. And this is what you get, right? So this is going to be 1 minus the factor here that it's being powered to the k. And this is to the power of n plus 1, and then in the denominator you get this. This is just an expression that comes up all the time, and we need to be familiar with it. Otherwise, you can just check it out in this appendix I just mentioned. Great. So we have found a relation between the total volume of the blood that it's sitting in the system and the volume that it's sitting in the aorta, with all of these different parameters there in hand as well. The interesting thing, somehow, is that if one takes n to be quite large, right? If these parameters are suitably small, and they are, then we can assume they are, then you can just approximate this like that. Basically, these will go to 0, and you are left with this term here. Basically, what this expression is telling us is that the total blood of the system is bigger than the blood of the aorta by a factor of 1 over 1 minus this term over here. Okay? Now this is a very good approximation, but it's telling something rather important, and it will be carried to our discussion here, which is the following. Basically, for any organism, the total amount of blood that sits in it is going to be directly proportional to the volume that the aorta can handle. Right? So this is actually it looks like we've worked a lot just to reach this conclusion, but this was necessary. And now we're going to do something just as we did before with the currents, with the fluxes. We are going to go all the way back from the volume of the aorta, and we're going to work back until the level of the capillars. How do we do that? Well, we know that if I define B sub C, just as before, this is the same as V sub n, basically the volume of an element of the capillary level, right? This is nothing but pi r sub n squared, just as we have done over here, but now we're going to go all the way to the last iteration of this self-similar process, times L sub n, right? But notice that this is but beta squared gamma to the power of n, right, times the volume of the aorta. If you don't see this straightforwardly, just think about it for a second and you'll see this is exactly what we have done here, but now going all the way to capillary level. Why am I going through this painstaking process of going again to the capillary level? Well, now that if I take this expression here and put it back over here, what I get is that this is equal to the volume of the capillars, right? The volume of blood that sits inside the capillars, times beta squared, gamma to the power of minus n. And again, remember what we said about the capillaries. The capillaries are bounded, they're constrained by fundamental fluid dynamic laws and also tissue dynamic properties, right, from each of the organisms. So this is basically a constant of the problem. This is a constraint that it's imposed onto biology from physics, if you want. Therefore, what we are seeing here is that because this is just a constant, we can just ignore it in terms of proportionality, and now we see that the total volume of the system, total volume of blood of the organism, needs to be proportional to this funny guy over here. So we've worked a lot just to reach this, but it needs to be done step by step. Okay, this is interesting, but it kind of is like not exactly what we're looking for. We're looking for a relation between metabolism and body mass. But we established before that the total volume of blood will be directly proportional to the body mass of the system. So with these two, now what we're getting at is that the mass of the system needs to be proportional to beta squared gamma to the minus n, where n is the number of iterations of this self-similar process of branching. Oh, but notice, just as it happened before, this is a dimensionful value here. Mass is in kilograms if you want, there's units. But beta and gamma, they are relations between lengths. So these are pure numbers. They have no units. They are adimensional. N is also adimensional. It's just the number of branches that there are in the system. So this is an adimensional value, and this is a dimensional one, and we need to reduce this. And so we reduce this again with the same constant, with a constant that basically reduces this m value over here. So basically, you could say that m over an m naught that reduces this dimension to basically adimensionality is going to be equal to this value. Finally, we can take logarithms, just as we did before, and we find that the logarithm of m over m naught is just minus n logarithm of beta squared gamma. And this is another interesting relation that we've obtained from looking at the system as a self-similar fractal system. We're getting closer to the end now, but I want you to just for a second look at these two relations that we have obtained through this painstaking process. So first, we have this relation here that we basically obtained, remember, from assuming that the total blood of the organism needs to be proportional to the body mass of itself. Right? The other one, we were looking at something different. We were looking at flux conservation. Flux conservation gave us this relation over here, and since flux is related to the input energy, namely the metabolic rate, B, then we obtained this with this alpha constant here. But notice that now we could just, we could just take these terms here, isolate them, so logarithm of m over this reducing constant m naught, right? And make these two equations equal so that we reach some sort of relation between alpha, n, q, and then these self-similar parameters beta and gamma. If you do so, if you take these two equations, you just equal them where you can, you will reach the following, right? So basically log of m over m naught will be n over alpha log q, and that's equal to minus n log beta squared gamma. Notice something magical is already happening here, right? Because remember, n was one of the parameters of these equations, and it just told us how many branching processes do we have to undergo through, right? But now, for the relation purpose of these different adimensional constants, q, beta, and gamma, and also our main idea here, which is alpha, getting this alpha value, this is no longer required. N just cancels. So it looks like it doesn't really matter how many branching processes you went through, as long as they were many. That's something that we use there. So, okay, we could just rearrange this a little bit, just to make it a tiny bit more elegant, and we see that alpha here is going to be minus logarithm of q over logarithm of beta square gamma, right? So we're going to take this expression here, and we will go a little bit further now in order to simplify this beta and gamma in some terms of q. And as we will see, we can do that with the two ansatz that we've established in the first term, and reach a final answer for what the value of alpha needs to be. Great. So far, with all of the scheme that we established, we arrived at the following expression. We said alpha, our aim, our goal exponent here, we want to understand, will have to have something to do with this q, which remember is the branching number, beta, which is the relation between the different radii for each of the branches, right? And gamma, which is the relation for the different length of each of the branches, right? This is very interesting. This is a fascinating expression, but we need to arrive at a number at the end of the day. Sure, all of these are pure numbers, but we need to see whether this is indeed 3/4, as Max Kleber predicted already from experimental data in 1932, right? So again, in 1997, what West, Brown, and Enquist came up with is the idea that, okay, so if this is a space-filling fractal, if these circulatory systems, right, that basically vascularize all of the organism, and they are the actual root of the problem here, because that's where the energy input is kind of like distributed, or how it is distributed. Therefore, the metabolism needs to have some relation here. But if this is a self-filling fractal, what can we say about this? And this notion is a bit difficult to grasp, but imagine that I now go and look at the aorta of my system. So I look at the aorta and I say, okay, the aorta has like some specific length, right? But the idea is that this aorta, through its branches, it needs to be supplying all the blood to all of the body. So somehow it makes sense to say that the volume that the aorta supplies, somehow, it's in a good approximation, the sphere, okay, the sphere that corresponds to the diameter being the length of the aorta. Okay, so what I'm saying sounds a bit strange, but if you have studied fractals before, you know that this is the kind of process that you would see in any space-filling fractal, be it, for example, a Hilbert curve, etc., where you have some specific enclosed area and you keep filling it by iterating more and more. But if you look at the first 0th order iteration, what you say is that the volume of that this system enclosed should be looking at something like, okay, so if this would be, for example, my aorta artery in this schema here, in this picture, then the volume that this is enclosing, right, should be all the volume of the system. And now, don't take this too literally, just think about what I'm trying to say. So, if the volume that this is enclosing as the sphere that stems all the way out from it being its diameter, then what happens next is that in the next iteration, basically, I am having exactly the same situation. The volume that it corresponds to the union of all the different volumes of the different branches, right, should be the same. Okay, remember, this volume is not the volume that sits inside, like we studied before. It's not the volume of blood, but it's the volume of all the cells that it needs to supply. And that's a bit of a difficult idea, but I encourage you to think about it, right? And if not, look at things like the Peano-Hilbert space-filling curve, which is doing the same sort of process in a mathematical way, but in 2 dimensions instead of 3 dimensions. And I think there you will get the answer to what we are trying to do here. So again, remember that this was actually a question of optimization that it was posed in the first in the first half of this lecture, and it resonated with the idea that you were optimizing the supply, okay, the blood supply. Now we're going to define the following. So we're going to define V hat here, V tilde, as the volume of influence, right? This influence meaning this supply that will stem from a particular branch, right? So this is basically the volume of the volume of influence or supply that stems from a particular branch. So for example, the aorta, we are thinking the volume of influence of the aorta is the volume that is enclosed by a sphere, right? Which diameter is the length of the aorta. So the volume of influence of a particular element of a branch K will be the sphere that stems from thinking about this length of this branch as its diameter, and so on and so forth. So this volume, in general, for any value here, will be 4/3. So we're looking at the sphere, right? 4/3 pi, and then LK halves, because remember we are looking at L sub k as the diameter, to the power of 3. But also remember that if this is the volume of influence supplies per kth iteration, if you want, right? So this needs to be multiplied somehow by the number of branches that we have. So if you think, for example, this is the branch kth plus 1, and this is the branch k, so this would be branch k, and this would be branch k plus 1. What we're trying to say here is that a space-filling fractal, all it does is say, okay, this volume of influence is actually going to be the same as the sum of this volume of influence. Great, so basically what we're saying here by these ansatz is this, right? But now, if we put all of this together, remember this is just q to the power of k, because that's the number of branches that I'm going to have at the kth level. Right, so if we put all of this together, we'll have here 4/3 pi L sub k halves to the power of 3 equals to 4/3 pi L sub k plus 1 halves to the power of 3 times q, right? Because this is happening q times at the next level. So this equals to this one over here. And by doing this, we're saying that in each iteration, we are preserving the same volume of influence, the same volume that we are supplying to. That's the idea. Great, we can rearrange all of this. We can get rid of all the 4/3 and the pi's, etc. Also the 2's in the denominator. And basically, if you do this right, you'll get the following. Lk plus 1 over Lk to the power of 3rd is nothing but 1 over q. But remember, we've seen this before. Lk plus 1 over Lk was the self-similar element, gamma. So this gives rise to gamma to the power of 3 equals 1 over q. Great. This means nothing but gamma equals to q to the minus 1/3. So we have this now. Great. We're getting closer. Now we have gamma in terms of q, and all we did was assume that this needed to be a self-similar filling volume. Now, what's the other ansatz here? Remember, the other ansatz was talking about the economy of tissue. You want to have somehow minimize the number of cells that you need to in order to build up this system. And in order to do that, basically what you say is, okay, so if I'm plugging here this I'm inputting here this flux, basically when I branch it, with whichever number here, I'm using 3 all along, but it could be anything, right? What I'm going to say is that the surface here, the section of this pipe, is going to be the same as the section of these 3 different pipes. Somehow this is like a balance that basically allows you to equilibrate the total number of cells needed. So in other words, you are economizing the tissue that you require in order to build up this system. So if we do this, basically what we're saying is this section here, which could be the section at branch K, if this would be branch K and this branch K plus 1, if this is section at branch K plus 1, what we're saying here basically is that Sk should be equal to Q times sk plus 1. Just as we did before here, right? Well, here the definition was a bit different because I was including the q inside, but it basically is the same idea. Now we will have this relation. But this gives rise to this relation over here, right? And again, this had something to do with the self-similar construct that we have been building our system with. In fact, this is the parameter beta. So here, what we see is that beta squared equals 1 over q, or if you want, q to the minus 1. And I'm actually not going to simplify further. Sure, beta is q to the minus 1/2, but if we remember our expression over here, here what we find here is a beta square, so we will keep that. Awesome. So all we need to do is we take these two relations over here, we take our relation over there that we have encountered before, and now we are done. We just need to work a little bit farther, some little algebra here. So we have a logarithm q in the numerator. Here we have two terms, beta squared and gamma. We can separate them, but basically what we find here is this is log q to the minus 1/3 from the gamma, and the beta squared is just minus 1, right? Notice that this is minus log q, and this is going to go outside of the logarithm, and that's actually 4/3 with a negative number, a negative 1. So this is the term outside, log q, and something magical happens here, which is that now alpha doesn't even rely on the branching number, because this is cancelling away. Now the minus sign is also cancelling, and now we get that alpha is nothing but 3/4. Which is basically what they wanted to prove. And this is a very fascinating story. Now we have reached a number. This is an exact number that's telling us how the metabolism, remember, the metabolic rate scales with the body mass of an organism. This result works for metazoa and for plants, and actually it works in a very wide way, right? But now it's not just an empirical law, thanks to West, Brown, and Enquist. This is now something that we can understand mathematically. This model that we presented here today is actually the model by West, Brown, and Enquist, the first model that they presented. But there have been further simplifications, if you want, or other ways of approaching these processes via, for example, maximum entropy, that were also successfully giving the same exact result. So it seems that there is some universal process lurking behind these ideas, right? And all it had to do was basically thinking about distribution of energy. These sort of ideas have actually gone way beyond this. So for example, further work has been developing ideas on, okay, so if we have these sort of metabolic scaling laws, what can we say about replication rates? Do replication rates are replication rates constrained by the fact that we need to supply energy to the different cells? Other great ideas correspond to, for example, growth. So we know that growth needs to be supplied with energy, right? And if you think about the supply of energy being constrained in this way for different organisms, then we know for sure that growth will always have some constraint being applied to their curves, right, over time. And this is also observed in nature, and it's also very elegantly put in terms of these metabolic scaling laws. Not only that, but further questions have been now started to being tackled with these ideas. There's a great book by Jeffrey West himself, who's one of the authors of the seminal paper that I have here sketched out. This book is fascinating. I think it can be read by any person who's interested in complex systems. It goes way beyond these ideas over here. Some of them are still being discussed. It talks about technology, evolution of cultural evolution, and many other topics. I think it's a fascinating read, and I truly recommend it. And with that, I just want to remark the fascinating process that these ideas underwent. Remember, we started in 1932. Some data was there. We saw the data kind of fit this law very perfectly. So there was an empirical law that turns out to have like some 0.75 factor there that we couldn't understand why, but that kept people thinking and thinking and thinking, and many decades later, people took this problem again and put it pieces by pieces, put it together, and found that this is actually something more remarkably universal, and something deeper was underpinning all of this process, right? And I think this is one of the greatest achievements in complex systems, among many others, but surely it's one of the ways of thinking that we want to pursue in this course.